In this video, we're going to discuss how to find local maxima and minima along a function. First, a definition. The critical values of a function that is, are points along the function where the derivative f prime of x is 0 or undefined. And so just to visually get an idea of what that means, there's two options. The first is that the derivative is 0. So imagine if we had some function and let's say this was our function and it took on this shape. I would say this function has two critical points, or two places where the derivative would be 0. That would be this point here because that tangent line would be 0, and this point down here. So what we're showing here is two instances where we have critical points because the derivative, the slope of the tangent line, would be 0. The other possibility are places where the derivative is undefined. So let's look at an example of one of those. Let's say in this coordinate axis we had a function that looked like this. And you may be thinking, no, that's actually the absolute value function, or a type of absolute value function. It is. And so for this function, I would say this point right here is a critical point, because the slope of that point is not clearly defined. It could actually be multiple things. You could have a tangent line similar to this one, a tangent line similar to this one, but we can't just define one specific tangent line. So that's our two examples of critical points. Now, critical points are going to play a key role in finding local maximum and minimum. So first, a definition. If P is some point in the domain of a function, and let's say P, or the value of f of P, is less than or equal to all the values around P, we call that a local minimum. So just for example, graphically, if we had some function that had this shape, we would have a local minimum at the bottom of that parabola. So let's say that point was A. We would say it has a local minimum at the point A, comma, f of A. Okay, a function has a local maximum at P if f of P is greater than or equal to all the values around P. So let's say we had a graph of a function that looks something like this. Then at the top of that graph, let's say that occurred at x equals b, there would be a local max. So we'd have a local max at b, comma, f of b. It is possible for a function to have local maximums and minimums along it. And so what we want to do is figure out how can we find all those possible local maximum and minimums. So it's going to be important to note this. If you look at both these graphs, and in fact the graph of any function, the local maxima and minima must occur at critical values. And remember, this is where f prime of x equals 0 or is undefined. Okay, so the first way we're going to do this is what's called the first derivative test. And so there's a few steps to this test, and the first thing is to find the critical values. And then around those critical values, we want to look at what's happening to the slope. So graphically, let's say we had the following function. I would say looking at that function, we appear to have two critical points. So we would want to identify those critical points. If this point to the left appeared at x equals a, we would say that's a local maximum. The way we would know it's a local maximum is if you look at points to the left of a, the derivative would be positive because the function is increasing. If you looked at points to the right of a, the derivative would be negative because the function is decreasing. At x equals b, if we called this other point b, we would say that that is a local minimum. The reason it's a local minimum is if you look as you approach b, the derivative would be negative because the function is decreasing. And to the right of b, the derivative would be positive because the function is increasing. So let's look at algebraically how we can use the first derivative test to find all the local maximum and minimums. So the first thing I want to keep in mind is that we need the critical points, or the places where the derivative equals 0 or is undefined. So the first thing we need to do in order to do this test is to find the first derivative. So let's start first. F prime of x would equal 3x squared minus 18x minus 48, and then we'd have a 0 for the 52. So that's our first derivative. And we want to know where this thing equals 0. And so we're actually going to have to go back and use some Algebra 2 skills and use some factoring to solve this. So the first thing that I would say I would notice is you can divide 3 out of all these terms. Okay? And after we divide 3 out, the reason that's helpful is if I divide both sides by that 3, well, 0 divided by 3 is 0. And on this side, the 3 would go away, and I'd have x squared minus 6x minus 16. And we can continue to factor that. If I split that up, we want to think, how can we multiply and get negative 16 and add and get negative 6? I would say that would be negative 8 and then positive 2. And so solving each one of those equations, I get x equals 8 and then x equals negative 2. Those are our possible local maximum and minimums. Those are our critical values. So we want to determine if those are indeed local maximum or minimums. So I'm going to first consider x equals 8. And the way that I'm going to know if x equals 8 is a local maximum or minimum is I'm going to look at what the derivative is doing around 8. Is it increasing and going to decreasing, or vice versa? So I'm going to pick 2 points to the left and right of 8. So if I pick one to the left, like let's say x equals 7, and I picked one to the right, like say x equals 9, I want to see if the derivative is positive or negative around those points. So I'm going to plug 7 into the derivative function. And if I calculate that, f prime of 7 will equal negative 27. If we plug in x equals 9, f prime of 9 would equal 3 times 9 squared minus 18 times 9 minus 48. So f prime of 9 equals 33. So what you're seeing is that the derivative, the slope, went from decreasing to increasing at x equals 8. So what we have shown, x equals 8 is a local minimum. So we're going to do the same thing now, but we're going to consider x equals -2. So if we plug in well, really we want to pick points to the left and right of -2. So let's pick like x equals -3 and x equals -1. And we're going to plug those into the first derivative and see what the slope's doing around -2. So f prime of -3 would equal 3 times -3 squared minus 18 times -3 minus 48. So f prime of -3 equals 33. And if I plug in -1, f prime of -1 would equal 3 times -1 squared minus 18 times -1 minus 48. So f prime of -1 equals -27. And so what we've shown here is that around x equals -2, to the left of it, the function is increasing, and to the right of it, it's decreasing. So if you think about x equals -2, it has to be a local max. So x equals -2 is a local max. Now in this example, we're going to do some interpretations and again think about what that slope is telling you. So a company wants to track the rate of its production. The table below shows the production rate, P prime of t, where t is an hour since the observation was made. So we're not looking at the total production, we're looking at whether the production is increasing or decreasing. And we know that when the derivative is positive, the function is increasing, and when it's negative, it's decreasing. So if we look at this table and it says when is the production increasing, we're increasing whenever the derivative is positive. So what I would say is we are increasing during this stretch here. When 0 is less than or equal to t is less than or equal to 2. And we're increasing in another spot. We're increasing over here. So from 6 less than or equal to t less than or equal to 8. We are decreasing only during one stretch. I'd say we're decreasing during this stretch here when the derivative is negative. So we're decreasing when 3 is less than or equal to t is less than or equal to 5. And so if we want to know when production is greatest, well, recall you have a maximum whenever the function shifts from increasing to decreasing. So when does the function shift from increasing to decreasing? That's during this time. So when would production be greatest? Between t equals 2 and t equals 3. When is production the least? Well, we get minimums when the function goes from decreasing to increasing. So that would be during this time here where we shift from a negative slope to a positive slope. So when is production the least? I would say between t equals 5 and t equals 6.